Assalamu alaikum, everyone. So we will proceed with our lecture number 9, EE341, microelectronics. So what we are going to cover today, we will talk about two, based on the time permits, two main topics. The first one is regarding the differential pair, diff pair with active load. We'll see why we need it and how it's different from the other one and what is meant by active load. And second thing is common mode rejection and common mode rejection ratio. So common mode rejection ratio. So before we proceed, since at this moment I cannot see any of you, but just to link with the previous lecture, where you have seen in the previous lecture and did some examples regarding the diff pairs, and yeah, you have seen the diff pair with the cascode. So I will link from the last lecture where you have seen a differential pair with the cascode, and you try to do some examples related to that. So this is a common diff pair with a cascode, right? So here, since it's a symmetric architecture, what we meant by symmetric architecture, that okay, there is ultimately this point, if we say point P or whatever the name, it's ultimately a AC ground or a virtual ground. Since if signal increase here and decrease by the same amount, there will be no current, AC current flowing through this node P. So we can say this is an AC ground, and based on this property, we can separate like the right and the left hand, and we can solve any one of them, and that will be equivalent to my differential gain. So if we want to write the differential gain, previously it was V out by V in. For example, we can write for this part. Okay, so we can use these variables. So V out, let's say negative by V in plus. Okay, that will be equivalent to, so if we want to see, so there will be GM1 times, so it's going to be negative in any case. So it's GM1 times what's happening, the RO1 times GM3 RO3 in parallel with the cascode of the above one, which is being seen here from this point. It's going to be similarly RO7 times, if it's a GM5 RO5. Okay, because of the cascode, we saw this behavior is coming. And if we want to reflect it back, yes, the overall V out plus minus V out negative divided by V in plus minus V negative will also be equal to the same expression. But since we also say that GM3 is going to be identical to this guy, we are giving it name, name missing M4. So yeah, so it's going to be a GM3 will be equivalent to GM4. GM7 will be equivalent to GM8, and GM1 will be equivalent to GM3, and similarly GM5 will be equivalent to GM6. So that normally we take, that's why they are diff pairs and they are symmetric, and we can do this thing. So now that's what we have covered in the last lecture. But the beauty which we have seen in this configuration was something like this. We have an amplifier, which is the differential. It has two inputs, V in positive and V in negative. And we have two outputs, which are V out positive and V out negative. Okay, so that's something which we need to be careful. Now we have a differential pair, which is commonly known as fully differential pair, which has differential input and differential output. And that's well and good. We know how to do all the math, because it's going to be symmetrical and we can do everything what is going to be required. But what about this scenario? If, for example, we are using this instrumentation amplifier or a differential pair as an input, which is something like this one, input is again diff, but we want to connect it to some place, some block or some another stage or some other amplifier we call a programmable gain amplifier, which accepts a single-ended input. If my input for this next stage, whatever the next stage is, can be an ADC, can be a buffer, can be any amplifier, or can be my load, and I want that load for me to be a single-ended. If that load is a single-ended load, what's going to happen? If I can connect this diff pair, what's going to happen if I connect this diff pair, which I just have it now, that okay, this is my structure, which is a diff pair, and connect to another amplifier which accepts just a single-ended. So one way is ground this one and connect my single output to this single-ended amplifier. Okay, it will work. It will work, no issue. But I will lose all my information, which is important. I lose that gain for which I was having a differential output. So I will not get that benefit of achieving this thing. Why? If I just talk about only one node, V out plus or V out negative, they only give me half of that gain, not full gain. Why? Because this differential property, when this goes increasing and this goes decreasing, and ultimately when I do V out plus minus V out negative, my signal amplitude becomes doubles, right? And that property I'm not going to get here if I just use a single-ended point. So that's a drawback. So what we should do, we need to figure it out a way to how we can achieve a same gain from this differential topology if I just want to use a single-ended network, right? So that's what is the problem which we are having, and we will analyze it a little bit deeply now. So let's mark it and we can proceed further. So if I just want to draw the circuit, which we're just having a simplified model, not the cascaded architecture, rather just a simplified model with the help of a simple and NMOS and a PMOS as a current load, we'll see how it happens. So we have this architecture, which is here, So that's easy for us to give the names. And we can draw, we can say this is an M1 and this is an M2 for us. If these two are M1 and M2 for us, and here we have something which is a tail current, ISS, okay, which we normally call. And on upside, we are having a load, a PMOS current load. So we can draw the PMOS current load in similar configuration. This is a PMOS, and this one is going to be PMOS. As we know, both of them are going to share the same VB, like a bias voltage, so it makes our life easy. And this is a VDD, supply voltage. Okay? So we are talking about connecting these two outputs. This is, and this one, V out. If this is V in positive, this is V in negative. So this is going to be a negative output, and this is going to be a positive one. Okay? So now we want to connect this to a, if we want to connect this to a diff pair, that's totally fine. But if we want to connect to a single-ended, we need to see what should be the best way to connect that thing. So that's something which we need to solve out. So how we proceed further? If we just go with another topology, which basically give us benefit, is something like this one. I will just draw it again, but just for the sake of that one and just drawing it, if we just short this one like a diode connected and don't take this output here and use this as a single output. This is my, and this is a single-ended amplifier, let's say. If I do this configuration, analysis says, result says, ultimately somehow this V out positive divided by V in plus minus V in negative will be equivalent to almost the same gain which we were getting from the previous configuration. We are going to see this thing in a couple of moments, how we can figure it out, but that's what happens. Right? So this circuit, by just bringing a very small variation of this diode connected, it gives us a significant benefit. Let's draw it and then try to analyze it. First, let's analytically, and then we are going to go deep into the analysis sort of stuff, how we can derive that relation mathematically using a small signal model. So let me again draw that circuit, so how it works for us. Meanwhile, anytime you have any question, you can ask or you can just send an email, even we can sort it out. So here up we have a PMOS load. So again, this is a PMOS. So the PMOS load is going to be shared. So that's why we just draw this common end. And when we draw this thing, here we have our diode connected. On one of the sides, we have a diode connected, and I'm going to explain why we are doing this thing. The rest, everything is the same. So we have now ISS, which is a tail current. We can give the names to them. This is M1, this is M2, this is M3, and this is M4. And still, M1 will be identical to M2, meaning width and length and everything is same. GM1 will be equal to GM2. Similarly, the width and length will be equivalent. WL1 will be equal to W by L. And similarly, if we talk about M3 and M4, they will also be identical, meaning GM1, GM3 will be equivalent to GM4, and the width and length of 3 will be equal to each other, right? So that's what we can say. Right, and where are our inputs and outputs? Let's write in different colors. So here's, I'm just writing in the form of a V in plus, and here a V in negative. So now analytically, if we see which terminal we should take for an output, if I just like want to guess something, I know this diode connected is going to be 1 over GM3. If I want to see from this point, this is going to be 1 over GM3. So something moving from 1 over GM3, this means the impedance is going to be low. I want a high gain. 1 over GM3 is going to make it reduce. So that's why logically I cannot take output from this point. So I cannot take output from this point. No. So this is the point where I should take an output single-ended, which I'm saying an V out. So I take an output V out and feed it to an amplifier. Okay, a single-ended amplifier, we are feeding it, and we are still getting the benefit of the differential topology, right? So that's what we want to do. And then this V out will be, now the V out is going to be with reference to ground. So we are going to say this V out with respect to ground. Now, if we talk intuitively, we need to have some observations based on that which we can analyze this circuit properly. So we need to have some observations before we can analyze this circuit a bit more proper. So let's first work on those observations, and then we will move and we'll come back to the circuit. Crystallized circuit ko we can dive deeply into this implementation. So for that, for time being, let's do this one thing. So I'm writing first observation here. Yeah. So observation number 1, if I just don't add this circuit, for example, remove this M3 and see how my system is behaving by any variation at this point, V in plus, how this V in plus is affecting this V out. So let's draw this simple topology. So if we have this one, which is an NMOS, so I'm not doing anything, and this V in plus here, I am ignoring what's being drawn here altogether. I'm not concerned at this moment about this thing. What I'm concerned is something like this one. In negative, and this is my V out, because my whole analysis is to find, okay, how V out is being affected by V in variation is being increased, is being decreased, how the things are happening. So if V in goes up, since it's a diff pair, definitely the opposite side V in negative will go down by the same amount, which we know. So V in will go down. So V in plus is going up, V in is going up, and V in is going down. So if V in negative is going down, we want to see what's going to happen with this guy, V out. And that's something important. Again, at this moment, I'm analyzing it independently like a superposition. I'm not seeing the effect of M1 that I'm going to bring in a while. But if I bring V in down, what's going to happen? We know that V in goes down, the current ID will also goes down. So let's do V in negative goes down, ID goes down. As ID goes down, what's going to happen? The current is reducing. What will happen with the V out? We all know this thing that this is V out. There is a some PMOS connected here, okay, with some VDD. So now the voltage drop is going to be less, so that V out will go high. So one analogy we can do, as V in goes down, ID will go down, and ultimately V out will go up. So that's something which is an inverting behavior. We can also see in terms of this is V in is a common source amplifier, nothing else. With a load, with an active load is there. So if V in goes down, what's going to happen with the V out? Inverting amplifier, common source, V out will go up. So that's also makes sense for us that this is one thing that V in has an inverting behavior. As V in goes down, the V out goes up. That's first approach. What about the second thing? Now we, at this moment, intuitively, we ignored the effect of or this M3 guy. So now let's bring back that M3 and then see how this M3 is going to affect the overall system variation. Let me draw that one. I'm just drawing on this point. The circuit is going to be, again, this is a PMOS for us. This PMOS is connected to something VB, and this VB is going to be here. So that's somehow another topology, and then this is a current mirror. This is just a reverse of whichever we have drawn here. It's just a reverse of the same thing. So let's give any name, M1. Again, these are names are not like any relation with these names. I'm just writing some names that, okay, these are some transistors. And here is some current I. If, for example, we are feeding this current I and we increase this current by some amount, delta I, what's going to happen? This is a current mirror. So we have a current mirror here. So this I will also increase because they are in series. So more current will flow through M1 and they are in diode connected. So this is a current mirror. So whatever the current is being increased at the M1 will also see the increase in a M2 side. So here ultimately the current was increased. Because of that increased current, what we are observing, the M2 will be also having more current. Again, the current will go up, but as the current will go up, my output will again be going down. So that's what, again, the same thing. Current is going up and ultimately my output will be going down. But I am seeing at this moment in terms of an opposite configuration where the current mirror is from the NMOS. Okay, so that's what you need to see. It's not like all the time it's going to be the same thing. Here, what's happening, we need to analyze the circuit. The current is going to be increased. Because of the increase in the current, ultimately, we are observing increase of current in M2. And because of this increase in the current, this is again an active load. And ultimately, my V out will go down. But if we see the opposite scenario, which is being shown in the screen in our desired circuit, what's happening that now we, let's say the current mirror is a PMOS load, which is something which we are observing, but you can have any circuit in your analysis, but let's say which is at this moment we are analyzing it. So if we want to draw this circuit, let me draw it here. So here the VDD goes up, and as the VDD goes up, this is again a current mirror formation. Down we have current. Now let's see, this is a current I, and here we have an NMOS, right? So this is an NMOS where we are applying a VB something, and what's happening with the V out with an increase in current, because we want to observe the behavior. So this is similar to what we have seen here. If I want to point out, they both are similar. So you can just see this analogy is similar to that one, even if I can write this is, let's say, an M2 and this is an M4. This M1 is a current source and this is a current mirror, M3. So exactly similar. So now if the I is increased, I becomes I plus delta I, meaning we have some more current. More current will be fed from this point to M4. And as the current is increased here, what's going to happen? Now this time it's a current load. It's an active, it's a current. Output is here. So what's going to happen with the V out? V out will go up. So because of this increase in the current in PMOS current configuration or PMOS current mirror configuration, my output is going high. In this case, it was going down, but here with the increase in current, it's going high. So that's some phenomena which we need to also be careful. Also, if we want to see in a different perspective, okay, this is a current moving from here. The current moving from here is also increasing. So this current is increasing. Because of this impedance, this VB will be reduced. If VB will go down, this is again, what is the configuration for us? A common source configuration. So this V out will go up. So anyway, we can analyze even in the small signal analysis or the large signal analysis, both ways. With the increase in the current here in I plus delta I, my V out will go up. Now what I am going to do, I will just reflect back these two approaches, which is, let's say, this one. I'm writing 2 here because we are using this approach here, and the first approach of impact of M2 and impact of M1. So this overall configuration is impacted by 2 current paths, one falling from M1, M3, and M4, and other because of the variation of M2. So let's draw it and try to see how we can analyze it. So if we would just want to draw it again intuitively, but we can see that, okay, our overall circuit is something like this. M1, M2, okay. So these M1 and M2 are the 2 currents. So ISS. Here we are applying, again, this is a positive side, so I can say I'm applying something V in plus. Here I'm applying something V in negative. Okay. Here what we are going to do, we said, okay, there is something diode connected, so it's going to be like this. This is going to be my source, okay. And also above, we are going to have some PMOS load, which is being controlled by this point. And that's something which I want to also bring some notion now, why we are controlling this point like this one and why some variations are coming. So this is M2. So this is M2, not M4. This is M2 and this is M3 and this guy is M4. So now there are a couple of points which we need to make at this amplifier. First thing, the naming convention before we move forward now. So now we are seeing the circuit. So the naming convention is something which we are calling it as a differential amplifier with active load. So what is meant by active load? We are using a current mirror here, which all of you can observe. This is a current mirror. M3 and M4 is forming a current mirror, but this time it's not acting the current mirror which we use in a normal topology. Meaning we are not feeding a constant current. This current is being changed or being governed by this M1. So M1 can go up, M1 can go down, and because of that variation, which is going to happen because of being in plus and being negative, the current will go up and down. As the current will go up and down, the current at M3 will change, and correspondingly, the current at M4 will also change. So that's why it's actively changing, and that brings the name active load. So we are having a configuration in which the differential amplifier having an active load. Okay, so that's why यहाँ जो terminology active load की है, that you all need to understand that it's active load because it's varying at dynamically, varying at runtime. The second thing, I would like to rub these things because I want to draw. Yeah, the second thing which is very much important. Now we need to see there are two behaviors which we already saw. If I1 changes from here, so this loop which is I'm drawing here in red color is going to impact. Agar yahan se V in goes up, what's going to happen? Current will increase. We all know I plus delta I will happen. So there is some plus delta I. Because that's plus delta I, current will increase here, and which we just saw in a phenomena, the V out will go high. So V in plus increase the V out. So V out will go up. The second phenomena, at the same time, the V in plus is going high. We also need to see what's happening with the V in negative. V in negative is going down. I'm drawing with the blue color. So V in negative is going down. That is the property of diff. The differential same amount increase on the V in plus, same amount decrease in the V in negative to analyze the behavior. So if V in goes down, we just saw in the previous page that if V in goes down, since it's a simple common source topology, the V out will go also high. And please make sure to understand, pause the video, go back, make sure to clear this point, because that is very much important, that both of these trends are ultimately increasing the V out. From M1, M3, and M4, a positive increase is coming, a non-inverting behavior is coming, whereas from the M2, a inverting behavior is coming. And ultimately, both of them will make your V out high. So ultimately enhancing the gain because of this two loops. And that's basically assist that ultimately, instead of using a two differential outputs, how those two differential outputs support to have a equivalent gain comparative to that previous, like a fully differential approach. That's basically the main idea, or analytic analysis. One more important thing which you also need to make sure at this point, in previous designs, we say, okay, this is a symmetric network, the differential pair. But in this case, this is not a symmetric architecture. We cannot draw a line, separate the half and solve it. No, we cannot do this thing. Why? Because M1 and M2 are symmetric, agreed, but M3 and M4 are not symmetric anymore. Why? If we see the input impedance at this point, that's going to be 1 over GM3. Whereas what's the impedance here? RO4. They are not symmetric anymore. Therefore, we cannot separate the half circuit and we can analyze it. We have to analyze the circuit in overall totality. And because of this not symmetric nature, this point is not AC ground anymore, which I just said in the first page that, okay, we have a fully differential pair and this point is AC ground or virtual ground. So in this case, this is not an AC ground, not a virtual ground, because there is some variation which is going to happen. So we need to see it analytically, and we call this point as a P. Again, P, any name which is going to be any node which we are going to use, right? So again, if you have any confusion till now, make sure to cover it, make sure to go back and then proceed forward, because this concept of two loops, of one loop of M1, M3, M4 having a non-inverting behavior and M2 of inverting behavior is very much important. You just don't have to remember it. You have to analyze it and you have to counter question yourself, because we can have any other behavior. Ultimately, just when start mein dikhaya tha, we can also have a PMOS structure and an NMOS current mirror. In NMOS current mirror, the scenario is going to be opposite. This M1, M3, and M4 are not going to behave in non-inverting, rather it will also behave in inverting architecture. So you need to see which behavior and how you are going to analyze the circuit. So for that, you need to make sure the two loops concept, that how they are enhancing the V out ultimately is clear to all of you. So make sure to clarify this point. You can also read the book. Book is written nicely, but the book is explaining these things a little bit earlier in the BJT part. In chapter 10, if you go for the differential amp with an active load, so the book first talks about the BJT and then talks about the MOS. So since we are talking about the MOS only, so if you, let's say you read the MOS part and you don't get this thing clear about the two loops, you can go one page earlier and read through the BJT, and the BJT is explaining this two loop part very much clearly. And that's basically ultimately the concepts and the things remain same. So let's move forward towards analyzing these two behaviors. So for the analysis of these two behaviors, we can have some derivations. And for those derivations, we can just draw again a nice circuit and we can move forward. So what I will do, I will just use another page so that we don't mess up things. And for those things also, I will draw again a circuit, and I will also give you some like a question to think over it, how the things are linked, and you get an idea about that stuff. So let me redraw the circuit for you, so you can just get an idea about things. So let's do a small circuit before moving forward. So again, if we just save this thing, we have, this is something which we are just observing. Sorry, this is not going to be, so that's going to be something which we are seeing a PMOS. So we are having one PMOS here, we are having another PMOS here, and that's we said it's a diode connected. Okay. This PMOS is diode connected, and here we have an NMOS. Okay. So we have here NMOS, and we just want, again, before moving forward, we just want to analyze, okay, there is some variation because of M1 has increased his value. इसको मैं VB कहता हूँ. Again, I'm just doing a little bit before proceeding further, a little bit a sanity check again that we all are on the same page. So this M2, I'm using these names M3 and M4, and this M1 basically have some variation, or VIN has some variation. Because of that, the current increased by delta I. Now we all know the current increased by delta I. Ultimately, the V out on this part will go up. We are only again seeing the behavior with respect to I plus delta I. So if there is a delta I increase, the V out goes up. Now, if we want to observe this point X, so what's happening is this point X. Let's analyze this point X because of this delta I variation. How much voltage variation, or how much voltage change you want to say, or voltage variation is noted at X because of this delta I increment. That's something which we are concerned point. X में delta I की वजह से कुछ variation होगी, and that will be reflected to V out. So if we want to see this M3, we all know we can replace with a diode architecture. So we can replace simply with a 1 over GM, if it's 1 over GM3. And if you want to have an accurate model, okay, you can have an in parallel RO3, but approximately this is going to be equal to 1 over GM3. Assuming lambda is 0, or 1 over GM3 is smaller pretty much than RO3. Okay, or this GM3 RO3 is bigger than 1. Whenever we say greater than 1, the factor of 100 should be suffice to do to cover up this thing. So what will be the delta Vx if this node is here X? So the variation will be definitely delta Vx. So the delta Vx will be, we know the current is flowing the delta I, and the delta I is going through 1 over GM. So delta I times 1 over GM3. So that will be the variation which we will note at this point. So that is clear that, okay, delta I by GM, which we can observe the variation. But the interesting thing is that what is the variation because of this small change at the point delta V out? And again, try to ponder, try to pause the video and try to see that thing. What will be the delta V out here? So we need to see analytically again, what will be my delta V out at this point? Just don't directly jump into the points, but see what will be my delta V out. If we analytically see this point now is delta Vx. So small variation at this point is being reflected on the point of V out. So this will be converting into delta V out. So if I want to write the relation of delta V out by delta Vx, I can easily write something similar, which you have also done in the quiz and also in your previous lecture. But we can divide that circuit and we can see the delta V out by delta Vx kya hoga. Again, keeping these two M4 and M2 terminologies, it's again a simple common source, and we have a load of M2, which is going to be RO2. So if we want to do the simple math, it will be minus GM4, since it's a inverting amplifier, times RO4 in parallel with RO2, right? But what we are interested, what's the small delta I did variation to delta Vx? So we can also find out delta V out will be equal to delta V out equal to minus GM4 RO4 in parallel with RO2 times delta Vx. If we do this thing and if we just plug in the values, minus GM4 will be RO4 in parallel with RO2 times delta I, which is directly proportional to it, and 1 over GM3. From that analogy, we also know that GM3 is equal to GM4. That's what we all the time make sure, meaning width and length are the same current is flowing. So we can cancel out these two things. In ideal environment, again, that's going to be RO4 in parallel with RO2 times delta I. And that will be again inverting. So if we want to talk about the overall variation, delta V out will be something like this. So that's significant as compared to simple one. So we have a good amount of variation which is happening because of this delta I variation. And interestingly, what's happening, this effect of M3 is totally cancelled out. That 1 over GM factor, which was basically reducing the value, which was reducing the gain, is cancelled out. 1 over GM3 is nowhere in the delta V out. And that's very much interesting effect, which we want to observe. Again, till now we have seen analytically how this behavior, but now let's move on and see how in this overall architecture, which is a differential with an active load, how the things change. So let's draw again the circuit and make sure, okay, you should also draw multiple times so you get to know this behavior. So what I'm going to do, I will draw the circuit and I will draw the small signal model. Since we cannot divide into two, so we have to draw the small signal model of the overall architecture. I would highly recommend all of you to not only just see the video, and it will definitely easy to understand things, but you need to make your hands dirty. Until you will make your hands dirty, you will not get an idea, or you will not be able to translate the things to other similar problems. So let's again draw that one, which we just have. I will try to squeeze this one so I don't take much space so that I can draw the small signal model. So this is again the active load, which we are saying because of this, we normally given an active load. We have an, now this is back M1, V in plus, V in negative, again M2, V in negative. I'm just mentioning it as a point P. So for this is M4, let's say this is M3. And let's draw the small signal equivalent of this thing. Okay, so yahan se, and with this point, we are going to take the V out. And we are interested ultimately to find V out divided by V in plus minus V in. Now we want to prove that relation. Okay, we said that this is equivalent to the fully differential amplifier gain, but now how? We have to analytically, we have to rather prove quantitatively. Analytically, we have seen the behavior of this two loops. Okay, this loops help and this helps, but now we want to see, okay, quantitatively, small signal model, how it's helped. So we can draw the small signal model. So I'm liking this black color more, so small signal. Right, so yep. No, as I mentioned at this moment, M3 and M4 are PMOS, you can observe. So this M3 and M4 are definitely the PMOS, and M1 and M2 are NMOS. Changing them, we can definitely change them, but then the topology will be different. If you want to apply input to a PMOS, then the PMOS will be definitely on top and NMOS will be connected to ground. So the configuration is going to be changed. If you come early, or if you can go back later on when I upload the video, we have analyzed this. If you see this two circuit, we also see what is going to happen if we use an NMOS current mirror. Definitely based on that circuit topology, you need to analyze what's the correct pattern. But currently what we are doing, we are having ultimately NMOS as an input pairs, and M3 and M4. But whatever is going to happen, we cannot do this thing. M1 and M2 are, for example, NMOS, and M3 and M4 will be NMOS. No, that's not possible. Why? Because we want to feed the current, and when the current is going to be fed, it's going to be VDD. Or otherwise, if we want to do the opposite, then we have to sync it. And then in that case, the M3 and M4 can be NMOS, but then M1 and M2 will be PMOS. So ultimately, they will be vice versa. Either the input pair will be NMOS and current mirror will be PMOS, or input pair will be PMOS and the current mirror will be NMOS. So in this configuration, we are using these as NMOS. So let me, if I want, I can write it. M1 and M2 are NMOS, and M3 and M4 are PMOS. So for source of PMOS is all the time connected to VDD or the highest potential, and the source of NMOS is connected to ground. So there is no separation. The bubble sign also shows it's a PMOS, and without bubble is NMOS. So all of these things are the same. So let's draw the small signal model. Small signal model doesn't change, so it's not going to affect. Just will. So the arrow sign will be different, not current arrow size, not more than that. So I will draw it, and if there is some confusion, please feel free to ask me. One second. Solve this circuit using M1, M2 as a PMOS and M3. Yes, definitely we can do, but let's have the one variation, and then you can just do that thing. I guess that shouldn't be an issue. I don't know, like we already did for the opposite scenario. But if you want, we can do that thing. But let's have one first conclusion, because nothing is going to be changed in the small signal analysis. I can draw that one even now, but I don't know, like there's no such benefit which we are going to have if you just want to draw that. So for example, I can draw, because the small signal model will remain the same ultimately. So I can just draw that for you. Yes, exactly same. Gain will be exactly same. Nothing will be varied on the gain, right? If, for example, you want to say the expression will be the same, but then you say, okay, for the PMOS, the GM values can be different than NMOS. Yes, that can be small variation, but ultimately it's totally going to be same. If you want the expression, if we want to talk in terms of expression. So let's do this thing. I will do that thing, and you can just try on your own. And if you feel any variation, you can tell me. But at this moment, I will just draw the architecture, how the PMOS architecture will look like. So the PMOS is going to be like you, for example, again, I'm writing the M1 and M2, but these are the PMOS now. Okay. So here, these are the PMOSs. So PMOS are your input ones. So these are the two sources again. Sources again are going to be connected to the highest potential. So here is the highest potential, which is basically we are using, and the current mirror are NMOS now, which we just also saw. So here NMOS, and this is NMOS. And at this point, here is the V out, right? So if you want to talk about configuration, this is again a ground. So you can see this is an NMOS for here. This is M3 and this is M4. So I just use this M1 and M2 vice versa. So overall, you can even see the GM1 and GM2 will come correspondingly the same way. And here we can just, instead of having that point P again. So ultimately, everything is going to remain same. So here you can just say V in goes up, and this is vice versa behavior. So there is no as such variation in the small signal analysis. So I would highly recommend all of you to even take this one and do that analysis, and if you figure out something different, just please update and we can look into it. But ultimately, the relation is going to be all the same. So my preference will be continue the same, and then if you want, we can also do that things. So let's draw the small signal of this one amplifier. So here we start from this point. So we in positive. So something V1 कहते हैं, we can say this as a V1. So current controlled GMP1, and then this is going to be G1. So this is this part. And then if we want to move forward, M2 will have RO2. And this is the same point P. It's not a ground. Just make sure this is not a ground part. This is a PMOS, which is this one. So which is a P point, which is an NMOS, but and also the current is going to be. I like to draw this current controlled source more like this fashion. So it's going to be GM2, V2, and if we just want to do it, this is going to be V in negative. Okay, so we have the V in negative. And then if we want to see this point and this point again, this will be V2. Okay, this is V in negative, and this point is this one. So that's the M1 and M2 we have drawn. Let me just rub, because I will draw up and I will write. This is a small signal, but I am just rubbing this thing. Okay, so if we want to draw on the top, what's happening, this node, let's give the node a name, for example, for easy visualization. This node is X, so we all know this node X is connected to diode connected M3, so we can replace with this one. So this is a point X, just to have, and this is equal to 1 over GM3. And again, I'm removing the RO3. Ultimately, RO3 can also be there, but for our simplification, I'm just removing it. We don't want to have an. And this is going to be now what? VDD, DC VDD, AC ground. So this node, we know that this is AC ground or a virtual ground. It's a small signal model. And what's happening on the other side, we also have this point V out. And V out, interesting thing, what's happening in this V out, this is negative, this is positive, and this is, if you want to say this potential V3, this V3 is going to the gate and drain of your M4, and that's controlling your rather it's opposite. So it's basically, let me just rub it. It's not like just you can write it, yeah. So here basically what's happening is VGS, right? Rather we give VSG value, so V3 is this potential, okay? VSG, okay? So if the VSG is here, we can say it as a VSG3. So we can nominate the VSG3 for our visualization, but we will show the current in opposite way since it's a PMOS. So what's the current? We can say, we can show it's GM4 times, everything else remains the same for the PMOS. We don't have too much worry, but what we can say that this value at this moment is equal to V GS3. Now, if you can see, I wrote this as VGS3 instead of VSG3. Why? Because I'm reversing the terminals to show this phenomenon. So I'm going to connect this thing and I can write this thing. This is my negative, this is my positive, and just I'm writing VGS3. Okay? The source is now virtual ground, or the source is AC ground. That's why I'm writing VSG3, and the potential is like this fashion. Okay? And this is, if I want to show opposite current, then it will be VSG3. Since I'm showing VGS3, the potential is something similar. Okay. And this is RO4. Okay. So that's overall, and they are connected at this point. So the ये terminal होगा, this terminal is known as V out for us. Okay. So if you have any confusion, you can just send an email or you can just look into it. But I will again recommend, try to draw the small signal yourself first and try to see any variation, any way you can have it. You know that current going through this, if it's an ID, opposite side, you can write an ID minus side. Okay? So any way you can have this configuration, make sure have your own analogy the way you are feeling comfortable with the things. Okay? Now what we can do, we can start analyzing that and we can have some namings for our own variation, and we need to, it's easy for us to apply some KVL or KCL, and that will benefit us. We can do like write all the equations and try to sort out the other way if we just see how we can get ultimate benefit, because our net goal is to find this expression. Okay, So how we can, this is V in plus, this is V in negative. How we can reach this thing? Let's a little bit go step by step. If we want to see this node, which is X, okay? So if we want to write the KCL here, okay? So at this node X, let's write the KCL. KCL at node X. If we want to write the KCL at node X, what's going to be? Let me write and then we can have it. The current leaving this node X is GM, this one current, GM13. So on the left hand side, I'm writing the current which are leaving the nodes. And then we have one current which is leaving also, which is equivalent to what this point, this node from this point to this is also VGS3. Okay, so this node is VGS3. So what the current also leaving is VGS3 by 1 over GM3, or we can write it directly VGS3 times whatever GM3 we can. Okay, so ultimately, and what else? And what else is that the current which is going to be flowing through this node. Okay, that's also leaving current. So we can see all the currents are leaving the point X. So if this is the point X, the current GMV1, the current from up from 1 over GM3, and the current from RO1, all of them are leaving this point. So we can write this current which is moving this point also here a leaving current. But what is the value of this current? That's interestingly which we need to write. We don't have to consider this a virtual ground, and this node we know is V. In this case, okay. So if you just, I will come back to this point, but let's Jamshed, what you are asking. If you see the left-hand circuit, that's more easy to evaluate this thing. This is what's the potential? VSG3. Okay. So this is a PMOS for you, and it's a current mirror. This current mirror is doing what? Setting the bias potential for M4, right? When setting the bias potential for M4, and we know this VSG3 as a current mirror is equivalent to VSG or a bias voltage for M4. So we can see that VSG3 equal to VSG4. And we know the VSG3, that's why we are using it, and we are replacing with the VGS4. Ultimately, यहाँ क्या होना था? Okay, good. So now where I was, I was writing this node point 1, which is at node X. So at node X, what we can write, this is my node, which is the potential हमें पता है, it was VGS3 minus VP, because there is a potential just from VP कह रहे हैं. We don't know its value. We will try to figure it out how, but ultimately we want to cancel it out. And then we want to divide by some potential, which is equivalent to R1. ठीक है? So यहाँ हम इसको ये कर लेंगे. So that is the, and this is all equal to 0. इसको equation 1 करें. KCL at node X. Now if we want to write the KCL at output, yeah, this is an output node. ठीक है? ये जो KCL है, यहाँ क्या होगा? Again, we need to write के current कहाँ जा रहे हैं. We need to analyze them. So first and the most important thing, if we just see this point, ये फिर मेरे पास वही VGS3 ही आ रहा है. So that's going to be VGS3 divided by this time क्या हो जाएगा? R4 हो जाएगा. 1 minute. Let me just see something. Naming wise. First, V out node पे the current which is entering is basically GM4 time VGS3. ठीक है? So entering current, again I'm writing it here. Entering current is GM4 times VGS3. Then plus, what's the other current? One current is V out by RO4. Okay, V out by RO4. That's another current. And another current which is also happening here is somehow for us is this point, which is equivalent to which is equivalent to this point. So that is equal to, if we just see this point V out, so these two currents are, we talked about these two currents are here, this is in this point, and then the leaving current for us at this node, just a 1 second. I'm seeing from this node at this point, the currents without this connection. Yes, so without this connection, the current at this point will be equal to VGS3. And again, for simplification, I'm writing it VGS3, and I will just bring it back the notion in a moment that how these things are linked with each other. VGS3 divided by whatever the GM3, so that will be equal to GM3. So we can just write the same expression. So it's also equal to 0. If we want to do simple math and try to find the VGS3 value, since we are not interested in VGS3, we can bring it back and forth and see this will be equal to minus E out divided by, I'm just writing directly, but if you can look for any mistakes, if I do, so it's going to be GM3 plus GM4. Or ultimately, what we can say that GM3 and GM4 are same to each other, so we can replace with minus V out divided by RO4 times 2. And I am just common because GM3 and GM4 are both PMOS, so I can use GMP. So that's another equation which we are interested. So we found the relation of VGS3, which is used in the 1. So I'm writing an equation 2. Okay. So make sure to just go through them. If there is some mistake, even if I did, or we can get to know at the end of the analysis whether we are doing fine. But the whole analysis that we need to write the KCL to make your life a bit easy. Hopefully we are doing fine. So if we do this thing, then what we can do, we can find the overall relation. We are also going to use this thing now. So there is another node which is left, so I'm going to write that one at a moment. So we write from the downside, now we are going to write upside, now we're going to write from the downside. Okay, so again the KCL at output from the other side, let me write it, let me correct it, which you are seeing. So it's going to be from the down, if you see, it's going to be current which is entering is ultimately GM2 V2, okay, plus V out minus VP. Might be this is what you are asking. VP is the same like a virtual ground, not virtual ground, is the P potential. So V out divided by RO2, which is here, and then this minus VGS3 divided by, again we can write it in the form of GM3 equal to 0. So that's somehow relation which we got. Now if we just combine or bring right and left, or the KCL at, this is KCL at output, and if we want to, let me from the last page, if I can write 1 second, the expression, or I will just bring it back. So the KCL at, which we wrote at X, was equal to GM1 times V1 plus VSG minus VP times RO1 plus VSG times GM3. Okay, so that's something which we, now if we just directly subtract these two or divide, whatever the way you want to, what we are going to left with. And also one more thing, RO1 is equal to RO2. GM1 is equal to GM2 is equal to, we can write GMN for our simplification, and here we can write RON. Okay, so जितने वो NMOS के हैं, since they are same, we can write RO1 RO2 is equal to RON, and GM1 is equal to GM2 is equal to GM9. So if we just do the subtraction of these two, so we can write, we are just subtracting these two, subtracting. So it's going to be I'm subtracting this one, like it's writing this is A and this is B, so I'm writing A minus B. Okay, so it will be GM1 rather, yeah, I GM1 को GMN कह देते हैं, and I'm writing V1 minus V2. So I'm writing B minus it. So that we want to get that expression of V1 minus V2, which we are interested. Plus, if we want to write V We just told VP will be cancelled out. You can see this thing. VP is going to be cancelled out. Why? Because the VP RO1 is equal to RO2, so we can simply cancel out VP. So ultimately, we will be left with the expression VSG3 minus V out, okay, divided by, I'm writing RON, plus again GM3s are same and VSG3, so it's 2 times minus minus plus 2 times VSG3 times GM equal to 0. Right. So RO1, RO2, let me just go back. Yep. So M1 and M2 should be equal to each other because we are talking about the diff pairs. Diff pairs, the property of the diff pair is that all both sides, width and length, GM should be exactly equal to same thing. Otherwise, this is not a differential pair. Okay. So this all the time in a diff pair, whenever we are going to design, M1 and M2 should be equal. I guess in the previous 1 minute, let me go in which slide I mentioned this thing. Yep. So here I mentioned, for example, all of the time, whatever we are using diff pair here is GM3. Yeah, M1 and M3. So all of time, these two should be equivalent to each other. There was a typo. Let me correct it. GM2 because this is M2. Okay. So all of the time in the diff pairs, whenever we are talking about left and right, all of them has to be equal to each other. So GM1 should be equal to GM2, GM3 should be equal to GM4, GM6 should be equal to GM5, and GM7 should be equal to GM because they are diff pair. Otherwise, we cannot proceed with the diff pairs. Okay. So इसीलिए M1 and M2 are equal. So GM1 is equal to GM2 and RO1 is equal to RO2. Another way you can also see, normally in one process, lambda n is going to be same. Okay. Same current is flowing. We are assuming it's a diff pair, so same current is going to flow. So lambda n will equal to same. So RO is equal to 1 over lambda ID. So for NMOS, the RO, if the current is the same, they should be the same. Since the GM is the same, the current is going to be of the same value. So, okay. So if we just want to now proceed and we want to see how the relation comes out, we can see this V1 minus V2. What is this thing? So that's a little bit open up. कि हम लोगों ने जो draw किया था V in, वो क्या था? V in 1 was in reality was V in minus VP, and V in 2 was equal to V2 minus VP. How? Again, let's go back and see this expression. But I am saying that जो मेरे पास V1 है, which is ultimately this potential, V in plus यहाँ है, और V1 is that potential which we are applying. So V in, sorry, let me just. So what I am writing is ultimately जो मेरे पास V in plus है minus V in, that is equal to V1, sorry, that is equal to VP, right? So this potential and same thing on the opposite sides. So now if we want, ultimately what we want in the expression in the form of V in and V in negative, not in the form of V1 and V2, because the input जो हमारे पास apply हो रही है, that is V in plus, not V negative. So यहाँ से हमें क्या पता चल रहा है, जो एक हम लोगों ने virtual ground की लेते थे, so it's not, in this case VP is going to be cancelled out. So I can easily write, अगर मैं इसको लिखूं, V1 minus V2 क्या होगा, V in 1 plus VP minus V in 2 minus VP. So the VP will be cancelled out and I will be left with something which will be equivalent to GMN V in 1 minus V in 2, which is desired for me. Then something comes which is equal to VGS3, yeah, whatever the expression, VGS3 minus V out RON plus 2 times VGS3 times GM3 to 0. ठीक है, तो इसको हम एक बंद कर देते हैं. इसमें क्या होगा, we just need to replace the value of VGS3 जो हम लोगों ने पहले find की हुई थी. We can just replace simply that value and plug it here. वो value क्या थी? I will write it and then replace in the next page. So VGS3 जो हम लोगों ने find की हुई थी, that was equal to minus V out times or divided by ultimately जो हम लोगों ने कहा था RO4 2 times GM, उसको भी हम लोग GM3 and GM4, so we can write GM4, GMP. We can just replace with this one. So if we just replace in this expression, what we are going to left with, we're going to have something. I'll just do small math and you can just yourself make sure to make your hand dirty. So GMN times, again I'm writing the thing so it's easy for V in plus minus V in negative plus VGS minus V out divided by RON plus 2 times VGS 3 times GM 3 equal to 0. Okay, so that's what we got, or not GM3. We said let's write in the form of a GMP. Okay, so that's what we want, and now we want to replace this VGS3 by that expression. So we will be left with, and I'm just going to do also take it to the other side in the next step. So GMN, let's write it V in positive minus V in negative minus, if we just want to replace this expression one, so we'll be left with minus V out. I'm replacing this VGS3 with this expression, will be 2 times GMP RON times ROP. Okay, this one will be left minus V out RON. You can again tap for any mistakes, but I feel that should be fine. But again, all the time you're more than welcome to look for any mistakes by solving yourself, because that's the whole benefit of doing the things. Okay, and 2 times VGS3 and 2 V out divided by, let me just this it was 2 times was down. So 2 times down. So let's 2 V out. Hopefully I am not minus V out. 2 V out comes here. 2 times ROP times 2 times GMP. Okay, and this is GMP is also coming. Okay, so that's fine. Sorry. Now we can cancel out a term which we can cancel out for our relaxation. GMP will be cancelled out with GMP. 2 will be cancelled out with factor of 2 here, and we will be left with something. If we just do this, take the V out on the opposite side, that's our ultimate goal. V in plus minus V in negative. All V outs are negative, they will go other side, they'll become positive, and I can also take them common V out. So V out will be 1 over 2 GMP RON ROP. Okay, plus, okay, it's going to other side, 1 over RON plus, if we just see that, we will be only left with a 1 over ROP. I guess I just write 2 times factor of 2, it will be 1 time here, because I already incorporated 1 time. So so that's what we are left with. So what we can do now, if we just see a little bit analytically what's happening here, this is RON product of ROP times product of GM. We can negate this value, or we can ignore this value as compared to 1 over RON. Something similar, आप लिखें 1 over 100 plus 1 over 2. So you can ignore the value of 1 over 100. So well, that's what we can see. We can write an approximate relation since we just want, we're interested in to find how this behavior is looking like. We are 2, so we are left with 1 over RON plus 1 over ROP, or V out by V in क्या हो जाएगा हमारे पास, V in plus minus V in negative will be equal to GMN divided by, ये क्या हो जाएगा, this means RON is in parallel with ROP. That's what we wanted. क्या हो रहा है, GM is being multiplied by the parallel combination of N and P, and that is similar to almost fully differential gain. जो हम लोग पहले derive कर चुके हैं. So here is the beauty of this active load differential pair, that it is the gain ultimately is equivalent to the single-ended gain is equivalent to the fully differential, and we can easily use it for loading any single-ended pair, and it still has an input differential pair, an input differential side. So that's the benefit of differential pair with active load. So if you have any questions, query, make sure to ask, make sure to send an email or come in the office or attend the next lecture. But what we are going to do, we are going to take from the same point where we finished today, and we are going to continue towards the common mode rejection ratio in the next lecture. But I will highly recommend all of you to go through this derivation one time. That's again, small signal analysis is very much helpful. This is all covered in your book too. So you can go through the book too, but make sure to do the thing intuitively. As something similar with Jamshed was asking, if you have any confusion about how you will deal with the PMAS, though it will be everything will be exactly similar in a small signal model. But if you still have some confusion, make sure you make your hand dirty one time, because otherwise it will be difficult to analyze any circuit with some small variation, right? So what we'll do, we'll upload the lecture, and if you have any question and query, you can ask and try to come in the lectures, because ultimately it will a little bit start hurting you as we go a little bit deep into the content. So you can ask the questions, at least you have this time, you can ask the questions and we can try to answer it. And we had today agreed to have a tutorial session to have some problem solving and doing that quiz, but unfortunately no one appeared, so I was available. But next time, if you this slot of office hours also doesn't work for you, or if you don't want to solve any question, make sure also update ahead of the time so we can do some questions, like at least help you in your assignments or quizzes, right? So if there is no question, no query, we can just call off the recording, and you can, means whenever the recording is uploaded, you can just see and you can come up with any query. Wednesday and the Thursday office hours, or in the next class, you can also ask the questions, right? And thank you very much.